assignment number 7, which is the penultimate of the assignments, is up now, and it's due on 2 weeks from today. And it covers material that we'll be doing in today's class and some of the multi-scale material. After that, there's be one more assignment, number 8, and it will be on the geometric transformations material, rotations, translations, perspective transformations, etc. in free space. It will be your first assignment that will actually have three-dimensional data. And that's the next topic after I finish today's lecture, or after I finish this material that we're starting today. And it will be up well before April 12th, that is to say 2 weeks from today, but we may not finish the material on it until then, or maybe the one class before that. The last class is on a Tuesday, and that last assignment, number 8, will be a shortish amount of time for you all. It'll be a little over a week, so that I can grade it in time for you to get the grades back by the last class, so you can ask questions on things that were exposed in that last assignment. The final exam will be take-home open book, just like the midterm was. You will again get multiple days to do it, but its due date will be determined by the formal exam time for 9:30 Tuesday, Thursday classes. So if you look up when those, on the unc.edu website, there is a list of final exam schedule. It says all Tuesday, Thursday classes have their exam in a 3-hour period between such and so and such and so and such a date. And the midterm will be due at the end of that 3-hour period. Okay? So you now can plan for when the exam, it'll be out for you for a few days before that due date. Any questions on, yeah?
I think it's May 3rd, just for
May 3rd?
Yeah.
Which is?
The Tuesday.
Tuesday, okay, so that's the Tuesday after the last, 1 week after the last class. I'll hold some final office hours after the last class, in the couple of days after the last class, and then after those office hours, the exam will be made available, like on the Thursday or the Friday before that Tuesday, something like that. Okay, in regard to the present exam, if Sakai works the way we understand it to, you will be getting later today your own scores on I call the raw scores on the exam. And I will be posting on the Sakai site the answers to the questions. I ask that between now and Thursday you look at those answers and compare them to your own, and come on Thursday with questions, yes, this next class, on this coming Thursday, with any questions you have on why was this the right answer and why wasn't something else the right answer. Okay, so I'll take questions in class on that on Thursday. I admire Scott Halliburton for having identified an error in one of the questions. It turns out that the fourth derivative of a Gaussian, say with sigma equals 1, is between 2 and 3 and not less than 2, as I had intended for it to be. And so I will not grade that question, that part of that question. It's a single, well, on the exam it's a question. But the way I have it, had it written, it was a part of a question. But in any case, so that particular question will be given 0 credit, except Scott will get extra credit for it. Any questions on any of that? Any questions on anything? Okay, till now we've been talking about interpolation methods, truly interpolative. That is to say, it was assumed that the data points were accurate. And you wanted to therefore have your approximating function, the function that you're using for interpolation, to actually pass through the data. But very often, in fact more often than not, data points are not accurate. You start out with an image and the image has noise in it, right? You have something based on various kinds of measurements, and the measurements have some tolerance. And so we're talking about images where the points are a value like intensity as a function of multiple dimensions. But in this picture that I'm drawing, I'm just showing a one-dimensional result. And the point is that you can think of the data points, which are the dots, as having error bars on them, right? They have a tolerance, which is some probability distribution around those, and this may be plus or minus sigma in that probability distribution. And for those, it makes no sense to insist that the approximating function actually pass through the points. They need to pass near the points, right? And ideally near in the sense of within the error bars, but not necessarily through them. And so the topic of today's lecture is so-called approximative methods, where we're still trying to find a function that we can evaluate at any place we want to interpolate, right? We may want to interpolate at, this value of x, and we're going to have some function like this dashed function that we can evaluate at that x. But the function need not actually pass through the given data points. They need to somehow pass near it. And there are two methods that we're going to talk about that have this property of passing near but not necessarily through the data. And one is called the successive subdivision or successive refinement method, and the other is called least squares. And we're going to be covering both of those in today's lecture. Okay? So the first of the two methods that we're going to talk about is the successive subdivision method that has a very interesting relation to the B-splines that we talked about. It turns out to be a rather easier to compute version of something that yields about B-splines. You'll see why I say about in a minute. And the whole, I've already given you the reference of Elaine Cohen's book on modeling with splines when we were talking about B-splines. But this method that we're talking about is also covered there. And it's due to couple of computer graphics experts named Ed Catmo and Jim Clark, so-called Catmo-Clark method. I have known both of them, but most especially Jim Clark. Jim and I were co-organizers of a visualization conference, a graphics conference, some years ago, and our names are on the proceedings of that together. I'll tell you I think a fun story, but a missed opportunity by me from that conference. Since I was co-organizer, I was the chairman of the first session of the conference. And the first presentation was by a Dr. Who. And I realized only after I introduced him that I should have said who's on first. For those of you who don't know the reference, go to look up Abbott and Costello, who have a very classic comedy sequence about baseball, and there was a Mr. Who was on first. Anyhow, and just to go further, I was on a Southwest Airlines plane, and the pilot came up before and told a couple of riddles. And one of them was in the Baseball Hall of Fame, the museum there in Cooperstown, New York. There's two statues at the entranceway, and he said, those two statues belong, as being appropriate for that Hall of Fame place, and they never played baseball, and they never managed baseball, and they never owned a baseball team. Who were they? And the answer is Abbott and Costello for that very enjoyable sequence. It's on YouTube. You can find it if you've never seen it. It's fun. Okay, anyway. To get back to the main point, the basic idea in splines, as you will remember, is that you have a grid of control points, okay? And they're regularly spaced. So the successive subdivision is going to depend on the fact that the xi are grid spaced. That is to say, they're regularly spaced. Least squares one does not have that requirement. Okay? And so I'm showing here in the diagram over here. This diagram here, the circles are the control points. And at each control point, we have a value, for example, an image intensity, right? And the basic idea is to move from the spacing of the control points to half that spacing. Okay, so in your assignment, you'll have data that is 16 pixels apart. And the first step is to produce a new image of control points that are 8 pixels apart. Okay? And this method is going to be used iteratively, successively. That's why it's called successive subdivision. Because once you have the ones that are 8, you treat them as control points and you subdivide again, and now you'll have data that are 4 pixels apart, and so on. And you can keep going successively, right? But I'm going to talk about right now is one level of the subdivision. Okay? And so the basic idea is that in a little patch of 3 by 3 control points, those circles, you want to compute the little 3 by 3 black points, which are spaced exactly half apart. And you'll notice that one of them, the center one, this guy here, is on top of one of the circles. And this not being an interpolative method, the value of the dot, the subdivided value, the value of the function at the center point in the dot is not necessarily the same, normally not exactly the same, as the value in the circle, the control point at the same point, right? And then what happens, if you think about a section, a subsection of the whole grid of control points, for this particular control point here, this circle here, we're going to compute the blue x's. Not the positions, but the values, the control values at those. And for the next guy down, the next control point, we're going to compute its surrounding 9 values, which are these red ones. You'll see that these overlap with these. And the whole setup is organized so that you interpolate the same value whether at these points, whether you're doing it from that control point or that control point. And so if you're going to have to write a program to do this, and if you want to write it most efficiently, you won't double evaluate those. But if you wanted to double evaluate them, you won't get any different result. I mean, if you do it for one center of control points, and you just iterate, just pass through all control points. Likewise, for this control point, you're going to compute these pink x's, and those again are going to overlap be the same values there, right? But when you finish, if you look at what's happened here, you're going to have a whole grid of subdivided control points, right? And the one thing you probably going to become aware is that there's nothing between here and here in the subdivided value. If these are at the edge of the control points, the left edge or the top edge, you're going to get the subdivided image is going to be slightly narrower. There's going to be a missing edge, if you will, in this result. But as long as you are concerned with anything but the results at that edge, you're going to get a new, call it image, a new set of control values at all the half specified points, and then you're done with that level of subdivision. Any questions so far, except for how the x's are going to be computed from the circles? The values at the x's are going to be computed from the values of the circles, which is going to be in an upcoming slide. Yeah?
Do both the approximative and interpolative methods use subdivision?
Catmo-Clark is not an interpolative method. Splines can be done. There exist splines that are interpolative, and I'll say something about that in the next slide. But the Catmo-Clark subdivision method that I'm teaching you is not interpolative, nor are B-splines. And, well, it's written on the next slide, but I'll tell you right now, it turns out that in the limit as the subdivision width becomes 0, the Catmo clock produces a B-spline result. Okay? And it converges pretty quickly. So after only a few levels of subdivision, you can think of it as a way of computing B-splines. Okay? And as you know, B-splines are not interpolative. Okay, but they are approximative. They are shift invariant linear operations, that approximation. And therefore, how can you evaluate the effect of this kind of successive subdivision? I've already lectured on that. Somebody should have learned by now. How do you evaluate any shift invariant linear operation? Yeah, you want to understand its effect on levels of detail, where for shift invariant linear operators, the natural one to use is the sinusoidal approximations, which are the eigenbasis of shift invariant linear operators. Okay, so we want to think of it as having a kernel and have the kernel having a filter, and the filter's in the frequency domain, and we can understand the effect on frequencies, and we can do this just as well for this method as we can for the truly interpolative methods. And it's not necessarily the case then that this particular method will be, more harmful at the high frequencies, more canceling out or lowering the image information at the high frequencies, at the small levels of detail, than an interpolative method might be. If you wanted to compare it, you'd have to go look at that filter, right? Okay. Any further questions from this slide before I go on? Well, I'll just say one more point, and that is if you wanted a value at some place like that, that you wanted to evaluate your function at, because you needed to interpolate that for whatever purpose, like after you're doing a rotation or a translation or whatever. But we talked about that. Well, the basic idea is the x's still wouldn't be good enough. Let's subdivide again. All right, one more level. And we get spacing a quarter of the original set of control points. Well, that's not close enough. So let's get subdivision again. And we get spacing an eighth of the original level. And notice that we don't need to stop at a spacing which is the original pixels spacing. We can go further than that. We can play the subdivision and get half pixel spacing, or quarter pixel spacing, or an eighth pixel spacing, right? By just doing more levels of subdivision. And once the spacing is such that one of the values we have is close enough to the location that we want, we can use that one. Right? Okay, so this is just to remind you that when we did B-splines, what was going on was that we were writing results as linear combinations of polynomials in the spacing level. The TIs were positions, in this case, of the particular subdivision level we're starting from at one stage of this. And so you can think of Catmo-Clark approximation as essentially successively using different spacing polynomials. And we've already talked about the possible use of splines in that successive multi-scale method. And so you can think of Catmo-Clark as doing that, right? If we have splines that are actually supposed to interpolate, we have noted that the ultimate coefficients of these polynomials as a function of the control point values, the control values, will be global. And as you'll see, Catmo clock is not global. It's going to compute it's going to compute this circle only a basis of the 3 by 3 region around it of control points. And so it can't be expected to be interpolative, and it isn't. Okay? Catmo clock is not the only successive subdivision method. There are others. One that's well known is after a man named Loop, capital L-O-O-P. It's not about loops in the code. It's about something that was invented by Dr. Loop. But anyway, the main point here is that we're talking in this course about Catmo clock as an example, and it's in fact the most commonly used one. And it is multi-scale, just as I've described, because it gives you an approximation at any of a number of scale levels, and you can actually take the differences between the scale levels at between the circles and the x's, the new x and the old is a value at the new x, little x is a value, and the value at the big circle is also a value. You can take the difference of those two. And when you take the difference of those two, you get a residue, and you can make residue pyramids, if you will, and do the kinds of things we talked about doing pyramids with this method. Okay, so here is the formula, and you're going to need this slide to do your homework. But let me just go through it for you. You start off with a square of 3 by 3 control points. The corner ones have values P1, P2, P3, P4. And when I talk about Pi plus 1, P4 plus 1 is P1, right? It's cyclic, mod 4, right? And likewise, values at not at the corners, but at the centers of the 4 edges of the box, V1, V2, V3, V4, with the same convention. And you also have a value at the center of that box, capital C. Clear so far? And what we're going to try to compute is the values at the 3 by 3 black dots, which are little c, little v1, v2, v3, v4, and little p1, v2. So p1, let's see what p1, little p1, little p2, little p3, little p4, and likewise, where's v1? Little v1, little v2, little v3, little v4, and center value c, little c. Clear? And now here are the formulas. The little pi's are the average of the 4 surrounding circles. The values at the 4 circles surrounding the box. No, that's not right. If you want this P1, it's the average, yeah, that's right, of these 4. Okay, so this guy here is the average of this, 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 and this. And this guy here is the average of this, 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 and this. Likewise, for this corner is the average of those 4, and here the average of those 4. Okay? That's the first step. So now you've got new PI values. The VI values have this interesting, which are 3/8 of the value at the center circle plus 3/8 of the corresponding V. So for this guy, that's the corresponding V. For this guy, that's the corresponding V. For this guy, that's the corresponding V. And for that guy, that's the corresponding V. All right, that's this guy. And then an eighth of the average of this guy and this guy for this guy, right, of the two corner values. For this guy, it's the average of those two corner values. And so on all the way around. And an eighth of the p-values that are associated with this. And so it's the yours and the next one around. Okay, so you now have a formula for the V's, and the C's, little c, is 9/16 of the old C plus 3/8 of the average of all the big V's around, plus a 16th of all the P's around. Okay? And you're done. You've computed all 9. You apply the V formula for 4 little VI's, the PI formula for all the 4 values of that, and the C value for that. And you'll notice that C is not equal to little c is not equal to big C. It's weighted by 9/16, but the other guys around are weighted also. So as promised, the new values at the pixel level, at the old control level, are not normally the same as their value at the previous level of subdivision. Okay? So you should be able to write a program from this guy, and after you do, you will get a new array with twice as many elements in X and twice as many in Y. And if you do this in 3D, you can play the same game. Essentially, there will be a new formula where things are surrounded by make-up boxes rather than, three-dimensional boxes rather than two-dimensional squares of control points. Questions? So that's the end of Catmo Clark. As I said, in the limit, as the subdivision level approaches 0, the grid distances approach 0, this does, in fact, lead to a way of computing splines. If you stop at some level, which you normally do, some level of subdivision, you won't exactly get what splines would have given you, but you get something quite close. B-splines I'm talking about, not any old splines, but B-splines, which are these localized splines. Okay. There's another method for getting these kinds of approximation, not quite interpolation, that have the very nice property that it's not necessary any longer for the control values to be in a grid. You can have an image space. Okay, this is X, Y, and you have data at miscellaneous points, which I will call any one of them X sub I. And you have a Y value at X sub I. And you're trying to get a function f of X that has this kind of behavior of being near the data and which can be evaluated at any position x that we want to interpolate at. Right? So I can call that guy y hat of x. It's a sum function, right, that you can evaluate at any x. I'll point out the notational ambiguity. Hat is used for two things. It means the approximate value at, or it means normalized value of. And it doesn't mean this, it means only one of those, and you have to understand the context which it is. And here it's the approximate value at. Okay? And the basic idea is here come basis images, right? Again, that we're going to try to find a y hat function, which is a linear combination of a fixed set of basis images, basis functions of x and y. And so we're going to pick this basis here beforehand, because for our particular problem, it works well. These are going to be global basis images. Polynomials are one of the most common basis images. And, you know, if you want to fit a third degree polynomial, the result is going to be a linear combination of the 0th degree basis image, which will typically be the function 1, constant 1. A second degree basis image, which might be just x. Well, and another one, y, if you have in 2 dimensions. So you have now 3 basis images, 1, x, and y. X meaning the x value at any point in the space of the image, y being the y value at any point in the image. And then, you know, you can use x squared and xy and y squared. That's 3 more basis images for a total of 6. Okay, and not going to be surprised to hear that if you wanted to go on to the third one, you're going to have x cubed and x squared y and xy squared and y cubed as 4 more basis images. Anyway, you're going to have some chosen number of basis images that we want to use. Okay, and if we wanted to use third degree polynomials, then I just did 4 plus 3 plus 2 plus 1. What's that, 10 total basis images that we're going to have pre-chosen. And let's call those basis images psi sub I of x. I better be careful here with my notation. This should be a j. I'm using j to index the data and I to index the basis images. Okay? And so what we're trying to do is at the data to get the difference between the approximating function f and the data to be small. And I will note in passing that if we have different tolerances, we'll want to divide each of these squares by sigma squared, where sigma is the tolerance level at the ith point. Okay, so that places that have very low tolerance get big weights, 1 over sigma sub I squared, and places that have big tolerance get lower weights. But I'm not complicating the story here. by this weighting function. All the sums will end up with the weights in there if we get complicated. So the idea is to find the set of coefficients of the basis functions. We're used to doing that, right? Which minimizes together this sum over all the data points of the difference between the approximation and the actual data value, yj. And so if f is of that form, I can fill in f this is just f at xj on left off of j. Let me put it in. So the size are evaluated at the respective data point locations. These locations here, positions are the xj's, the values there are the yj's. And you're trying to minimize that over the tuple A1, A2 up to AM. So if there are M bases, this is the number of bases. Number of bases. And N is the number of data points. Okay, so we have something that we want, a function that we want to minimize. And from your calculus, you should know that if you have a function of many variables and you want to minimize over those, you take the first partial derivative with respect to each of the parameters and set it equal to 0. For functions of one variable, you're certainly used to finding maxima or minima by saying the ordinary first derivative is 0. But if you have n of them, you want the gradient to be 0. That is to say, you want the derivative with respect to each ai of this function that I call capital F of a, not to be confused with little f. You're trying to get df by dai equal to 0 to get a relative minimum. Well, it could be a maximum or some kind of saddle, but it turns out that does indeed yield the minimum. And so, look, it's a bunch of calculus that you don't need to really have done. But if you take the derivative of this thing with respect to ai, you're going to see that it's going to give you a sum here. It's going to give 2 times this. Hence the derivative of the thing in parentheses with respect to ai. And that's just psi I. And that has to be equal to 0 for all each one of the AIs. And so it turns out, well, okay, I'm going to call that a K. And so it turns out that when you take that derivative and set it equal to 0, you get this equation. The sum over all the AKs times this thing in bracket times AJ, okay? And so let's call this thing capital AJK. The sum over all the data points times the psi j function evaluated at xi and the psi k function evaluated at xi, summed over the data points. That's just a number. I'll call it AJK. And so you now have that sum AJK equals this thing, summed over all the data points, that has a K in it. So I'm going to call that guy capital Y sub K. So we got, call that AKJ. And so we've got some AKJ AJ summed over J is equal to YK. Oh, it's just a linear equation in the unknowns, the AJs, right? So I get N, not N, how many K's are there? How many A's are there? You got M linear equations in M unknowns, and I can solve those linear equations, right? And so now I get the AKs. But wait a second, basis. How would we like our basis to be? Ooh, orthonormal bases is what we really have always seen has been really good. Okay, which is to say, what we want is that sum over all the data of psi I data is J, psi I of xj and psi, let's do it this way, psi k of the data runs from J, yeah, okay. Sum over all the data, psi k times, oh boy. Well, I've messed up my, okay, but fine. Psi L of xj should be equal to 0 if k is not equal to L, and should be 1 if k is equal to L. That's orthonormality, right? We're used to that. Except now the orthonormality is not over a set of grid points, but a set of arbitrary data location points. And if that's so, then these two terms cancel when j is not equal to k. So the bracket goes away, except when j is equal to k, in which case it's 1. And so you just get ak times 1 from this side, and some yi psi k of xi. And now it's really easy to solve those linear equations, right? All you do is if you have orthonormal basis, then you can simply multiply each data value times the k function evaluated at that data value, and you get the coefficient. Once you have the coefficient, you have this f, and you can evaluate it at any x you want because it's a linear combination of the basis functions. And so you can use this for a polynomial basis. Well, how would you make polynomial basis orthogonal over these specific points? Or you can use it for a sinusoidal basis. The psi i's can be sines and cosines at various frequencies, right? Or whichever set you want, but you have to orthonormalize them to allow you, once you want to do the interpolation, to get a really simple solution for the coefficients. Well, it's work to orthonormalize a set of functions. If you're going to do this once, I wouldn't spend the time. Live with 1 and x and y and x squared and xy and y squared. They're not orthonormal. They'll give you m equations, and my example of, I guess there were 10 of them up to third order polynomials. You'll have to solve 10 equations and 10 unknowns. The linear solvers are great at that. You just plug it into a program and it gives you the solution, right? But if, on the other hand, you have a situation where you're going to have, for the same set of data locations, problem after problem after problem, it's worth doing the extra work to orthonormalize the basis functions, the basis images, over that set of data once and for all. And then once you have those orthonormalized ones, you can use the one with the square around it, the really easy solution. So each time it's really, really quick. So let's just remind ourselves how you orthonormalize things. And as I said, by the way, the 1 over sigma I squareds come in every one of these sums over the data, if the tolerances are different. And the orthonormalization will depend on knowing the sigma I squareds at each point over the whole set of things you ever want to solve. But I'm not going to talk about with the 1 over sigma I squareds. But I can talk about the basis function. Okay, I'm going to have psi 1 of x being 1 at all x. Okay? There's nothing for it to be orthogonal to yet, because we're going to later get the first order ones and the second order ones and so on. But is it normalized? Somebody.
Is it not, because the squares don't sum up to 1?
Right. Sum of 1 squared over all the points I is n. How many i's are there? There are m of them. So that's m. Right? So, no, we don't want psi 1 of x to be 1. We want it to be 1 over m. Now it's normalized. Let's see. No, 1 over the square root of m, huh? Because when we multiply it by itself, the root m multiplies by itself. And you get m times m. Okay. So now we have psi 2 of x equals x. First order polynomial in x. And what we want is sum of xi times 1 over root m. I'll put the root m here, but it's going to come out. Have to be equal to 0. Right? Because we want it to be orthogonal, and that's not necessarily so. So we better not use x, but let's use a different basis function, x minus b, still a first order polynomial. And now we're going to have sum of xi minus b times 1 over m. We're going to want to set that equal to 0. And that's going to say sum of xi minus is equal to the sum of the b's, which is to say bm, because the sum I equals 1 to m is just sum of a constant is just bm. Okay, and so this gives us a solution for what b should be. All right, we can solve that for b. We we can plug that in here, and now we have something that's orthogonal to the first one. But it's not normalized. So we're going to need to figure out what sum of x minus b squared, xi minus b squared over I is. And going to have to figure out what its square root is to give us what the function is. It's not going to be x minus b, but it's going to be alpha times x minus b, and that'll allow us to solve for alpha. This approach goes under the name Graham-Schmidt orthogonalization. And we've got, okay, so now we have a polynomial in x that is orthogonal and normal, orthogonal to the zeroth order polynomial. It's a first order polynomial. Now we'll get another polynomial y, but no, you're going to want it to be beta y minus c, right? And you're going to want, you're going to want to do this same thing where you're going to want it to be orthogonal to this guy, orthogonal to that guy, and normalized. And you can play that game over and over again. Okay, and you're going to find out that no, that won't do because I got 3 conditions, and I only had 2 unknowns, the beta and the c. So I'm going to need also I want psi 3 to be alpha times y minus beta 1x minus beta 2, or better still, beta 1 times psi 1, which is this x minus b, plus beta 2. Now I got 3 equations and 3 unknowns, and I can solve for those 3 unknowns, and I get orthogonality and normality. And so for each one of these functions, I'm going to write it as its initial value, the thing we started from, minus a linear combination of all the previous ones. So that for psi 9, we're going to have, it's going to be the ninth original function minus linear combination of all the 1 through 8 basis functions, all multiplied by a constant. And the 9 orthogonality conditions with all the previous ones give us, what did I say? I guess they're 8. Give us 8 equations, and the normalization gives us a 9th. And so you have 9 equations and 9 unknowns. They're linear equations. You can solve them. And you get what the coefficients are. So you can successively build up basis, orthonormal basis, by this Graham-Schmidt approach. And that required solving a whole bunch of sets of linear equations. But once you've done it for once and for all. And as long as your data in successive problems is over the same points, you're in Fat City, and you can use those basis images, these new modified basis images, after you've orthogonalized and normalized them. And therefore, each particular solution is easy. Okay? This is least squares. And it works for any set of original basis functions. At least ones that the original set, the original psi i's, are not linear combinations of the other ones. And so if you want to do sinusoidal least squares approximation, you do it with basis functions that are sinusoids. If you want to do polynomial, you do it over basis functions that are polynomials. You want to do it over, basis functions that are e to the minus something or other, then you, again, solve that. As long as the coefficients remain multipliers of the basis functions and don't appear like if you had e to the well, I had my first job, summer job in medical image analysis, involved trying to do fit functions of the form ai e to the minus lambda I x, where you had to estimate both the ai's and the lambda i's to data. Because this was data that fell, well, it turns out it was t, but never mind. And now, as long as the coefficients that you're trying to evaluate are outside here, you're okay. If they're not, if they appear nonlinearly, like the lambda sub i's, then there's a whole new set of problems to minimize the sum of square error differences. And there's methodologies for doing, there are programs around for doing that as well. Okay? But for this course, we're assuming that the f of t's, the y of t's, are only have linear things, and these are not coefficients that appear non-linearly. I'll tell you a story about my experience with that problem. The moral of this story is academic learning buys you something. Okay, so I had a bunch of data that had these y values at various t values, and I wanted to find the ai's and lambda i's, and I was hired at a laboratory at Massachusetts General Hospital. This is while I was between my last year and next to the last year as an applied math major at Brown as an undergrad. And I spent a lot of time figuring out which method might be good. And I indeed came up with a method that was rather better than the ones they had started out with. But then I found that it didn't work very well. It didn't work well enough either. Oh, then I try to get a yet better method. I spent a lot of time on that. Later, I took a course in numerical analysis, and even later came here as a faculty member. This problem long since, pardon me. And I started teaching a course in numerical computing. I did that for many years, and in fact, I ended up writing 2 textbooks in numerical computing. They're both out of print, but you go to the UNC library, you'll find a couple of numerical analysis books by Pizer. One of them with a secondary author called Victor Wallace. Anyway, in it, I started worrying about what was called the condition number of a transformation. Condition number says, how does error get propagated between the data and your answer? Right? And so if your data are these y sub i's, and your answer are these a sub i's, these coefficients. This is a transformation that is independent of the particular algorithm that you use to compute it. Right? It's a transformation T that you're trying to go from a set of y sub i's to a set of a sub j's. Doesn't matter what algorithm I have, if my y sub i's are replaced by y sub I plus epsilon sub I, they have an error, then I'm going to have errors in so-called propagated errors in my solution. Right? And that's, there's an ideal solution T, and I don't care what algorithm I use, even if I solve T perfectly, but I do it based on this transformation from the y's to the a's, I'm going to propagate the epsilons into the deltas. And if that propagation factor makes the deltas 1,000,000 times what the errors in the epsilons are, it doesn't matter what algorithm you have. This is called the conditioning of the transformation. And then I said, wait a second, I had this problem I was working on all these years ago. This guy here, what's its condition number? Which is this error expansion factor. And the answer is enormous. So the problem I was given to work on, which was important from the scientific point of view in understanding, the problems were problems like how does radioactive materials that are injected in the body as they're taken out by one of the excretive organs like the kidney or the liver, how does the amount of that radioactive material stay as a function of time? That was an important problem for these people who were using these so-called radioactive tracers to understand the biology. But that problem has a ridiculous condition number. And even though I came up with some things that were better behaved than other methods, I was up against this condition number and I couldn't do anything about it, other than to recast the problem in the first place. Okay? This is just to remind you that all these things that we're talking about here in this situation of these approximations, the transformations have this propagation factor called the condition number, and it's worth your knowing what it is. That said, I've told you two ways to compute these approximations. One of them the Catmo-Clark method, and the other the least squares method. The Catmo-Clark method works only on data where the data points are in a grid form, and least squares is more general. Data points can be anywhere. End of section. Okay? We're now at the end of there are only two more topics in this, main topics in this course. Right? We began by talking about images and basis images, and started out with understanding derivatives. And then we went on to a section on shift invariant linear operators, and we saw bases that were orthonormal the sinusoids. And then we went on to multi-scale section, which had to do with being able to have localized basis images. And now we've done interpolation and approximation, and that is, we ran into basis images all over again. And now we're about to go to the last two topics. And the last two topics of the course are we'll call it topic N-1, is geometric transformations in 3D. And topic N is going to be ridges of images. And just the ridges idea is going to apply. We've seen edge images of edge strength, and we want ridges of edge strength, which are going to be the edges. Turn the edge strength image into curves along through the image that are edges. Or have bar strength, which are functions of position but also of width, and maybe of orientation. And we're going to, those bars that we're going to pull out of, for example, a pyramid are going to be ridges, and so on and so forth. So these are going to be trying to get the actual curves that are the edges of the bar centers plus their local widths and orientations or what have you. And that will be the last topic of these ridges. But now we're going to move on to geometric transformations. And I'll just show you the title slide of that section. If I can. Can't because the foolish Zoom system is fighting with me, and I'm not going to. It'll take me 2 minutes to get it back up. So I'll just wave my hand for a start. We're going to be interested in 3-space, and we're going to be interested in transformations like taking a 3-dimensional image and rotating it about some axis, or 3-dimensional images and translating it, or 3-dimensional images and scaling it in 3D. But we're also going to be interested in the so-called perspective transformation, where we go from a 3D image to a 2D image. So you all make a 3D image of your respective densities, for example, out there in 3-space. But when I see you in my eye, there's a projection so that when I see one of you and I see another one behind you and another one behind you, I get a projection all the way through the space, and it's all added up in 2D, projected onto my eye. I get a single 2D image on my retina. And so we're talking about those geometric transformations from 3D and how to compute them. And then when we finish that, you'll have a homework assignment on that. And then we'll get on to the ridges stuff. And you will not have a homework assignment on that, but you will have done some ridge things, more or less, by the assignments. What were they? The edge strength assignment and the bar strength assignment. Unbeknown to you that you were doing ridges. Okay, so we're done for today. And I'll see you on Thursday, and we'll start with these geometric transformations. By the way, they're on Sakai. The lecture notes for the next section is on Sakai.